Welcome to lecture 12. In this lecture we prove the basic results that we discussed about in the last lecture. So the first result says that suppose you have an m by n matrix A and a vector m vector B, then the linear system Ax equal to B has a solution U if and only if it is a solution of A prime x equal to B prime, where A prime and B prime, A prime is the matrix and B prime is the vector obtained from A B. You augment the matrix A by appending the vector B as m plus n plus first column, and then do elementary row operations. So let's prove this result. Look at this augmented matrix AB and obtaining and doing finite sequence of elementary row operations on AB, you get A prime B prime. Now write A prime equal to EA and B prime equal to EB, where E is the product of corresponding elementary matrices. Now E is a product of elementary matrices, therefore it is invertible. Hence, for any vector U, A prime U is equal to B prime if and only if EAU. So I substitute A prime by EA and similarly B prime by EB. So EAU is equal to EB if and only if AU equal to E inverse EB. You multiply both sides by E inverse. What you get is AU is equal to B. So therefore U is a solution to A prime x equal to B prime if and only if it is a solution to Ax equal to B. And that's exactly what we wanted to prove. Now let's look at the second result. Ax equal to B has a solution if and only if rank of the augmented matrix is equal to rank of A. Now to prove this result, first of all we can assume that the augmented matrix AB is in the row reduced echelon form, because we have already proved that if you do any finite set of elementary row operations on AB and get a new matrix, the solution to A prime B prime, A prime x equal to B prime is same as solution to Ax equal to B. So therefore we can replace AB by A prime B prime and assume that AB is in the row reduced echelon form. Suppose Ax equal to B has a solution. Now if there is a zero row in A, then the corresponding entry of B is also 0. Therefore there is no pivot in B. Hence rank of AB is same as rank of A. Now look at the converse. Suppose rank of AB is equal to rank of A, which means if you look at this augmented matrix AB and look at the 0 rows in AB that will lie at the bottom, because we are assuming that AB is in row reduced echelon form. So they will appear in the bottom, and wherever the entries in those entries, in the entries of A it will be 0, corresponding entries in B will also be 0. So, and that's the assumption that rank of AB is equal to rank of A equal to R, which means that there is no pivot in B. That is, B is a non-pivotal column in the augmented matrix. But now we have already seen that if you take a matrix in its row reduced echelon form, every non-pivotal column is a linear combination of pivotal columns. Now in pivotal columns are all columns of A. Therefore, B is a linear combination of columns of A, and that says that Ax equal to B has a solution. Now, if U is a particular solution of Ax equal to B, then each solution of Ax equal to B is given by U plus Y, where Y is a solution of the homogeneous system Ax equal to 0. That means, given any particular solution, U, every other solution is equal to U plus a solution of the homogeneous system. That's what we want to prove. So let U be a solution of Ax equal to B. Then AU is B. Now, for any vector Z, Z is a solution of Ax equal to B if and only if Az is equal to B. But then U is given to be a solution, which means AU is also equal to B, or in other words we can write Az equal to AU. But this happens if and only if A times Z minus U is 0, or in other words Z minus U is a solution of Ax equal to 0. So what we have shown is that if you start with a given vector U, which is a solution of Ax equal to B, then any other solution Z is of the form U plus Y. Here we can take Y as Z minus U. Therefore, every solution of Ax equal to B is expressed as sum of U and the solution of the homogeneous system Ax equal to 0. Now let's move to the next result. If R is equal to rank of AB, the augmented matrix, which is equal to rank of A, so the first two equalities, rank of augmented matrix is equal to rank of A, which is required for solution to exist for linear system Ax equal to B. Suppose this rank is strictly less than n. Then there are n minus r called unknowns, which can take arbitrary values, and other r unknowns can be determined from the values of these n minus r unknowns. This is something that we saw it while solving example 2 in the last lecture. The proof is essentially the same as what we did in that example. Let's go through the proof. So rank of A equal to rank of the augmented matrix, which is R, and it is strictly less than n. So since rank of the augmented matrix is equal to rank of A, it has a solution. And we can try to solve the corresponding system of linear equations. So we can get it, look at the homogeneous system. So the previous result says that any solution is a sum of a particular solution plus a solution to the homogeneous system. Again, because of the first result, we can assume that A is in the row reduced echelon form. In fact, the augmented matrix AB is in row reduced echelon form. Now there are R number of pivots in A and M minus R number of 0 rows. We can omit the 0 rows. I mean, they anyway do not contribute to the solution. From the rest, so write down the rest of the linear equations. Now move the non-pivotal variables to the right hand side and keep all the pivotal variables on the left hand side. So we will have the unknowns corresponding to the pivots on the left hand side. It is expressed as some linear combination of n minus r unknowns, which are on the right hand side. So on the left hand side we have these basic variables, and on the right hand side we have these free variables. So therefore every r variables on the left hand side is expressed as linear combination of the n minus r unknowns. So assigning values to each of these unknowns, the free variables, we get a solution for n minus r r unknowns, and we get the solution for Ax equal to b. So let's now look at result 5. If m is strictly less than n, that means the number of linear equations are strictly less than the number of variables, then the homogeneous system has infinitely many solutions. Suppose m is strictly less than n. Now we know that rank of A has to be less than or equal to minimum of m and n. So therefore rank is less than or equal to m, and it is strictly less than n. Now by our previous result, there are n minus r number of unknowns. Note that this n minus r will be at least 1. N minus r number of unknowns, which can take arbitrary values, and r other unknowns, the basic variables, are written as linear combination of these n minus r arbitrary values, free variables taking arbitrary values. Now each assignment of values to the n minus r unknowns give rise to distinct solution to the system Ax equal to 0. That means there are there is at least one free variable, and this free variable can take infinitely many values. Therefore you have infinitely many solutions for Ax equal to 0. Now if you have infinitely many solutions for Ax equal to 0, that means that you take any particular solution, that solution plus this infinitely many solutions will give infinitely many solutions for Ax equal to 0. I mean Ax equal to b. So if m is strictly less than n, the homogeneous system has infinitely many solutions. Now suppose Ax equal to b look at this system Ax equal to B. This has unique solution if and only if rank of the augmented matrix is equal to rank of A and it is equal to n. Let's try to prove this. Take R equal to rank of the augmented matrix and that is equal to rank of A. In all these, rank of augmented matrix is equal to rank of A is required to say that the system Ax equal to B has a solution. So suppose these two are equal, and that is if this is strictly less than n. If the rank is strictly less than n, then there are n minus r unknowns. This n minus r will be at least 1. Therefore, it will have infinitely many solutions. So Ax equal to B does not have a unique solution. If rank of the augmented matrix is equal to rank of A, which is strictly less than n, then Ax equal to B does not have a unique solution. Conversely, suppose rank of AB is equal to rank of A and that is equal to n. This means that A is invertible. Rank of A is equal to n. Therefore, it is matrix is invertible. R is less than equal to n and R is equal to n means R is less than equal to m. Therefore, m is equal to n and rank of A is equal to n. Therefore, A is invertible and hence the unique solution can be written as x equal to A inverse B. So this proves that Ax equal to B has a unique solution if and only if rank of the augmented matrix is equal to rank of A, which is equal to n. Now suppose if m is equal to n and Ax if m is equal to n, then Ax equal to B has a unique solution if and only if determinant of A is non-zero. And in this case, unique solution is given by x equal to A inverse B. This is an immediate consequence of 6th. If A is invertible, n cross n matrix, if and only if rank of A is equal to n, if and only if determinant of A is 0. And then just use the 6th result. Let's move to the last result in this set of basic results on linear systems. If m is equal to n and determinant of A is non-zero, then any solution is given, the unique solution is given by x equal to A inverse B, and it is, we can explicitly find out the jth coordinate, and the jth coordinate of this solution is given by determinant of A JB divided by determinant of A. Recall that the determinant of AJB, the matrix AJB is the matrix obtained from A by replacing the jth column of A with the vector B. So remove the jth column of A, put B there, and that is AJB. Since determinant of A is non-zero, by previous result, Ax equal to B has a unique solution. Call this unique solution y. So that means Ay is equal to B. Now this we can write it as y1 times the first column of A plus y2 times the second column of A plus etc. yj times the jth column of A plus etc. yn times the nth column of A, and that is equal to b1, b2 up to bn. Now take this vector b to the left hand side and combine it with the jth column. then what you get is y1 times A, the first column of A, plus etc. The jth term in the summation will be the vector yj a1j minus b1 plus etc. yj anj minus bn plus etc. yn times a1n etc. up to amn. So this says that determinant of this matrix must be 0. But then, if you recall, we were talking about determinant of aj plus u, aj of u plus v is aju plus ajv. Determinant of aju plus v is same as determinant of aju plus determinant of ajv. This is a property that we have listed when we talked about basic operations on matrices. So using that property, we can write yj of a11 etc. a1j up to a1n, an1 etc. anj up to ann minus a11 up to the jth column replaced by bi. Determinant of A with jth column replaced by B. And this is nothing but the second term is nothing but determinant of AJB, and the first term, the coefficient of Yj, is nothing but determinant of A. Now take determinant of AJB to the other side and divide by the determinant of A. What you get is Yj. So this concludes the proof of the 8th property as well. And we conclude this lecture.